All right, we're going to look at some properties for determinants. These properties are really there to help us compute these determinants and makes the computation easier. So they're not super essential to the grand scheme of things, but when you know them, it makes you a lot more efficient at computing them. So I've summarized all these properties in the next theorem. The first one is kind of a trick, is that if you have a matrix that is upper triangular, so upper triangular simply means that when you look at the diagonal of your matrix, so we have square matrices, so when you look at your diagonal of your matrix, if all the non-zero elements are above the diagonal, then we say it's upper triangular. If all the non-zero entries are below the diagonal, we say that it's lower triangular. And when we have such matrices, you can get the determinant very quickly simply by multiplying all the entries along the diagonal. So very, very quick trick. Next up, so that was for triangular. What about transpose? So if you have a matrix A and you transpose it, you're not changing its determinant. So the determinant of A is equal to the determinant of its transpose. If you have a product of two matrices, then it's the product of the determinant. So that's very useful if you already know the determinant of A and the determinant of B and you have to compute the determinant of the product, then you don't need to compute the product. You can just multiply the determinant. So that's for multiplication. For the inverse, it's not really a property. It's more a consequence of the previous one, because if there is an inverse for a matrix, so we know that A times A inverse, so here A times A inverse is equal to IN. So if you compute the determinant of A inverse, wait a minute, it's going to be the same as the determinant of IN. Because we know the determinant of IN is 1, we just get 1. And by using the product property, we know that the determinant of A times the determinant of the inverse is going to be 1. So if you isolate the determinant of A inverse, you get your formula that the determinant of the inverse is 1 over the determinant of A. The next 3 or /4 properties are really linked to the basic operations that you can do when you're using the Gauss-Jordan elimination algorithm. So what happens if you have a matrix, let's call it A, and that you create a new matrix by multiplying only one row or one column by a number k. So the operation would be row I becomes k times row I, or ci becomes k times ci. Then the determinant is multiplied by k. So this means, and make sure you see the distinction between these two, that if you are multiplying a matrix by k, then this means that you're multiplying every single row by k. So because of the previous property, since every time you're multiplying a row by k, you're multiplying the determinant by k, if you want to take out the k in the scalar multiplication outside of the determinant computation, you need to raise it to the power k, because there's k, because you multiplied n rows by k, and every time you're multiplying by k. So make sure you see that you raise the power of k by n. And this is typically the property that people kind of miss, that you have to, when you're multiplying a matrix by a number, you need to multiply the determinant by that number, but raise to the power of the size of that squared matrix. And then for swapping, so what happens if you're swapping two rows or two columns? Again, here we're saying for rows or columns, we're more used to work with rows than columns because of the Gauss-Jordan elimination algorithm, but it works for column too. Then the effect of this is that if you are swapping two rows or two columns, the determinant is multiplied by -1. And finally, but not least, so I'm going to use a different color for that one. What happens when you're doing an elimination on a row or on a column and you're transforming that matrix? Well, the beautiful thing here is that it's not changing the value of the determinant. And this is such a useful property. And I'm going to write a remark here. You can use elimination to create zeros in the matrix. And if you're familiar by now with determinant computation, you know that the more zero you have in a matrix, the easier it's going to be to compute its determinant. So if you know that, well, if you do elimination on rows or column, you're not going to change it. You're not going to change the value of its determinant. Then might as well do some elimination and create some zeros so that you can simplify the number of steps in your determinant computation. And for example, what I've done for you, if we go back to the example on page 23, where we had the matrix, where we chose column 3 to do our expansion, and then at the end we had two determinant of 3 by 3 to compute. If you are comfortable with elimination, you could say, well, if I take row 3 and I add 2 times row 1, so basically what you're doing here is you're using the 1 as the eliminator, and then you want to eliminate the -2, so you just create that elimination that is going to change the matrix but not the value of its determinant. And then you create this new matrix. So by doing row 4 is equal to row 4 plus 2 times row 1, you create this new matrix where the third column now has 3 zeros in it. And if it has 3 zeros, then you only have one 3 by 3 determinant to compute, and it makes the solution of this computation 50% of what it used to be. So, and you can double check here, I'll let you just try it, that you're going to get again the exact same value. So it's a very, very powerful trick. All right, let's do some examples of using properties to compute determinants. So first we have two matrices, A and B, and we first are going to compute their determinants. So for the first one, there's really nothing special. So if you just expand it, I use the second row. I got -106, so you can just do it as an exercise at this point. But what's really interesting here is the second example. The matrix B here is a lower triangular matrix. So if you just take the product of the entries on the diagonal, you're going to get your determinant quickly. So here, 4 times 7 times 9, and that gives you a nice 252. Now, if we look at the second example, so here, we're asking you now to compute a determinant of -2 times B transpose times A inverse. First thing to notice here is that we don't even know how to compute the inverse of a 3 by 3, so we're a bit screwed, but that's okay because we're going to use properties to compute its determinant. So the first thing that you do, and this is like the step that people miss the most or do incorrectly, is you take the 2 outside, but when you factor out the 2, you need to raise it to the power of the number of rows or columns. So here I need to raise it to the power 3. 3 because my matrices are 3 by 3 matrix. So the 2 is out, so you have the determinant of B transpose times A inverse. Now because B transpose and A inverse are two matrices that are multiplied, I'll use a product property so you can break this this product. So you get -2 to the power 3 times the determinant of B transpose times the determinant of A inverse. Now I'm going to, so that's just a product property, so the determinant of a product is the product of the determinants. So now I'm going to use two different properties at the same time. So the determinant of B transpose is the same as the original determinant, so you get -2 to the power 3 times the determinant of B, and then for the inverse, it's 1 over the determinant of A. And now we have our numbers, so we get -2 to the power 3 times the determinant of B that we freshly computed to be 252. 52 over the determinant of A, which is minus 106. You can leave it like this. I'll be happy. So now for the last two examples, we have a new matrix where for C, we took the matrix B and we did a swap between row 1 and row 3. So directly this means that when you're going to compute this determinant, you need just to multiply the original determinant of B by minus 1. So because the determinant of B is just 252, you just get minus 252. So doing one swap, just change the sign of your determinant. And now the next operation is we took the matrix A and we did a column elimination. And then if you're doing column elimination or any elimination in general, it's not going to change anything. So this matrix has the same determinant as the original matrix A, which is minus 106. And then you're done. But remember, elimination is more something that you're going to use to create zeros in order to compute your determinant.